Okay. Last time I asked you to find. First of all, we proved that the sum is equal to n times n plus 1 over 2. And I asked you to prove 1 square plus 2 square, to find a formula for this and to prove it, of course. The formula for this is equal to n times n plus 1 times 2n plus 1 over 2, if I'm not mistaken. If n equal to, oh yes, if n equal to 1, 6 over 6. Yes, this is the formula. How do we prove this? Let us check the formula for n equal to 1. For n equal to 1, we get 1 square is equal to 1. And the formula gives you, for n equal to 1, you have 1 times 1 plus 1 plus 2 times 1 plus 1. So you put 1 instead of n over 6. You get 1 times 2 times 3 over 6 is equal to 1. So they're equal. For n equal to 2. And sum formula. So for n equal to 1, they are the same. For n equal to 2, you get 1 square plus 2 square. So you have 4 more, 5. For n equal to 2, you get here 2 times 3 times 5 over 6. 2 times 3 is 6. They simplify, you get 5. It's also so. For n equal to 3, you have to put 3 square. You have to add 3 square to this. 5 plus 9, 14. Let's see what we find here. It is n equal to 3. So you put 3 here. 3 times. 1 more, 4. Times. 2 times 3 is 6 plus 1, 7. Over 6. This is 12. 12 over 6 is 2. 2 times 7 is 14. See, same thing. So how do you, so it's true for n equal to 1, for n equal to 2, for n equal to 3, but there are infinite many numbers, of course. You cannot check for all of them. How do you prove this? So you put this as follows. You assume that for n, it holds. You put it for n plus 1. You assume that the sum of 1 square plus 2 square plus n square is equal to n times n plus 1 times 2n plus 1 over 6. And you put that the sum of squares up to n plus 1, I think n plus 1 squared for this one, is equal to, here you put, instead of n, you put n plus 1. N plus 1. Instead of n, I put n plus 1. Instead of n, I put n plus 1. Plus 1 here, n plus 2. And then 2n plus 2, 2n plus 3 over 6. Assuming that this is called induction. Assuming that this holds, you prove this. Because we know it's true for 1. Well, if it's true for 1, then it's true for 2. Now that we know it's true for 2, it's true for 3. If it's true for 3, it's true for 4, and for 5, and so on. So it's true for all numbers. It's called induction. So let us check that. If this is true, then this is true. Capture both, please. So 1 square plus 2 square plus n square plus n plus 1 square is equal to. So I'm going to compute. I know the sum. I assume that the sum until n square is given by this formula. N times n plus 1 times 2n plus 1 over 6 plus n plus 1 square. So you put the same denominator, n times n plus 1 times 2n plus 1 plus 6 times n plus 1 square. You put 6 to here over 6. I take off n plus 1 out, n plus 1 times. So here we have n times 2n plus 1, this times this times this. This is 2n squared plus n plus I take n plus 1 out here, 6n plus 6 over 6. Everything over 6. Here we get n plus 1, 2n squared plus 7n plus 6 over 6. Is this equal to this? Well, I like this 6 here. I have the same 6 here. I like n plus 1. I have the same n plus 1 here. Well, this is the remaining part, this part, and this part. This is dubious. What do we get if we multiply these two? This is equal to n times 2n. It's 2n squared. 4n plus 3n, it's 7n. Plus 6, same thing. So this is equal to, so n plus 1 times, this is equal to n plus 2 times 2n plus 3 over 6. Okay. Any questions? This is called proof by induction. Can you hear me, first of all?
Yes, we can hear you.
Okay.
Can we look for the first word again, please?
For the first part.
First word, yes. Just for a screenshot, sorry.
Okay. So first of all, I guess the formula.
No, I understand, sorry. I just wanted to for taking notes.
Huh?
It's okay, I understand the question.
I see.
Wanted to take notes.
I see. Okay. First of all, in order to prove something by induction, you have to guess the formula, the answer. And this may not be so easy. It may be difficult, sometimes very, very difficult. First of all, it's not at all true that there's a formula for this. I mean, why should we have a formula for this? Somehow we have a formula. This is amazing part of nature, let's say. There's a formula for the sum of squares. It's not obvious at all, philosophically speaking. But there's a formula. How can you prove this? So let's say that this is Pn. So I want to prove P1, I can compute. I want to prove P2, P3, P4, and so on. There are infinitely many statements. This is for all n, for all natural numbers. For n equal to 1, for n equal to 2, for n equal to 3, for n equal to 4, for n equal to 5. There are infinitely many statements here. That it says that, for example, 1 square plus 2 square plus 3 square plus 4 square plus 5 square should be equal to, it says, you put 5 for n, 5 times 1 more, 6 times 2 times 5 is 10 times 11 over 6. The 6 disappear, 55. Is it true? 1 square is 1, 2 square is 4, 9, 16 for this, and 25. This is 25. 25 plus 25, 50, plus 4 plus 1, 55. This is amazing. Right? And how do you prove this? How do you prove infinitely many formulas at once? What do you do? First of all, you show that phi1 holds, that phi1 is true. Then you show that if phi(n) holds, then phi(n) plus 1 holds. One more. This implies that for all n, this is like this, phi(n). Because phi1 holds by hypothesis. But if phi1 holds, then phi2 holds. Now that you know phi2 holds, phi3 holds. Now that you know phi3 holds, phi4 holds. And so on. This is called proof by induction. It's very ingenious. But there's something bad here, something not so nice, is that you have to guess the answer. But there's a way of guessing the answer. There's a way. Actually, there's a formula. There's a formula for 1 to the k, 2 to the k, 3 to the k. There's a formula for all of them, up to n to the k.
Hocam, what's the meaning of guessing the answer? Like, we can calculate or compute the answer.
How do you compute? You can compute you can find 1 square, you can find 2 square, 1 square plus 2 square. You can find 1 square plus 2 square plus 3 square, yes. Yes, you can do this. But what about 1 square plus 2 square up to n square? And n can be any natural number.
Yes, so what's meant by guessing the answer? Like guessing the formula of the sum?
Yes, to guess the formula.
Yeah. All right.
For example, for the cubes, let's take for the cubes. 1 cube plus 2 cube plus n cube. Okay. Can you guess the formula? There's a formula. I tell you there's a formula. It's almost impossible. You will not be able to guess it.
Yeah.
Yeah, but I will tell you the formula, and you can check it for n equal to 1, n equal to 2, n equal to 3, n equal to 4, and you are more or less convinced that this is the correct formula, because first of all, you trust me, I'm not a liar, and then it checks out the first 4 numbers. It holds for the first 4 numbers. And the formula for this is n squared, 1 plus n squared over 4, which is the square of n times 1 plus n over 2. This is squared. And this number, as we have seen before, is the sum of the first n numbers. It's equal to 1 squared, I'm sorry, 1 plus 2 plus n squared. So sum of the cubes, sum of the first n cubes is equal to the sum of the square of the sum of the n numbers of the first.
Now I'm curious about the sum of the power of 5s, because now we can see a pattern showing between the odd numbers, the odd powers, like the power of 1 and power of 3 is the square root of the sum of the power 1. So maybe the sum of power 5 will be equal to the cube root of the sum of power 1.
I'm not sure whether I understood this. Are you saying the sum of odd numbers?
No, I'm saying that the sum of the powers of odd numbers, like sum of power of 1, sum of power of 3, sum of power of 5, and so on.
I don't know this. Okay,
It's
good
showing
question.
a pattern because
Good question. First of all, 1 is 1, which is 1 squared. 1 plus 3 is equal to 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. 1 plus 3 plus 5 plus 7 is equal to 9 plus 7, 16, which is 4 squared. In fact, the sum of all the first odd numbers, 1 plus 3 plus 5 and so on, until 2n plus 1 is equal to, let's do 2n minus 1, let's say here, 2n minus 1, is equal to n squared. This is very funny. This is very funny. This is very strange. This is one of the amazing facts of nature also. Why is this true? Okay, so this is 1. Okay, this is this formula here, 1. Now I'm going to add 3 more squares. I can add 1 here, 1 here, 1 here, 1, 2, 3. So 1 plus 3 is 2 squares, 2 times 2. Now I'm going to add 5 more. 1, 2, 3, 4, 5. 1 plus 3 plus 5 is equal to 3 squared. Now I'm going to add 7 more. 1, 2, 3, 4, 5, 6, and 1 more to close the gap. 7. So 1 plus 3 plus 5 plus 7 is equal to 16. Now you ask me 1 square plus 2 square plus 3 square plus 5 square. I have no idea what this can be. I don't know at all. Do I know it? Let us see. Let us see. Let us see. Let's look at 2 square. Well, no, I don't know. I don't know any formula for this. Do you know any?
no, not really.
It's interesting.
But I was wondering about another thing also.
Wait. You ask the last question. Let's see. 2 square plus 4 square plus 6 square, and so up until 2n squares. Okay. Let us see what this is. Instead of calculating the sum of odd numbers, let's calculate the sum of the squares of odd numbers. Let's calculate the sum of the squares of even numbers. Now, here this is equal to 2 times 1. This is 2 times 2. This is 2 times 3. And so on. And this is 2 times n squared. And this is equal to, I can take 2 square out. 2 square, 4. 4 times 1 square plus 2 square plus n square. Okay, this is easy. And I know what this is. This is equal to 4 times the number I found before. 4 times this. 4 times n plus 1 times 2n plus 1 over 6. Okay? Until, okay. Now I can find the formula for this. Let us say, let's go until 2n minus 1 squared. Okay? So this is going to be equal to 1 squared plus 2 squared plus until you go to 2n squares. You take all the squares minus the even ones. Minus the even ones. Minus 2 square, 4 square until 2n squared. Okay, so the sum of all the squares minus the sum of the even ones, you get the sum of the odd ones, right? So you get this, and this is equal to this. I know what this is. The sum of the squares. I know what this is. The formula is here. Where is it? The sum n squared is equal to n times n plus 1 times 2n plus 1 over 6. And here, instead of n, we have 2n. So I replace n by 2n everywhere. It is 2n, n, 2n. Instead of n plus 1, I put 2n plus 1. Here I put 4n plus 1 over 6 minus the sum of the squares of the even numbers. Here it is 4n times n plus 1 times 2n plus 1 over 6. Here we found the formula. You can do the same for
I'm really amazed by the genius approach.
it is not genius. It is not genius. Believe me, it's not genius.
Because you find a way to use the already given info we had in order to find the odd numbers.
Yes.
That's genius, I think.
Well, it's pretty clever, but it's not genius. It's pretty clever, and this cleverness comes from years of experience, my dear.
It's very clear. The experience is very clear, mashallah.
Thank you. And the second thing, of course, sometimes people panic in front of the students. A student asks a question, the teacher doesn't know the answer, and he panics. Well, I have an advantage that I don't panic because I don't care. If I don't know, I don't care. Okay. All right. But there's a way of guessing. I told you here, to guess the answer may be difficult, not so easy, but there's a way of doing it. And this is due to Bernoulli. He's a Swiss person, Swiss Jew, who immigrated from Holland, because of Spanish invaded Holland, and there was some anti-Semite movements in Spain, so they moved to Switzerland. So Holland lost a great scientist. Anyway, okay, I'm going to ask another question today. May I erase all this? Your last question. You have 3 dice. 3 dice. 1, 2, 3 dice. Let's call this dice A, this one B, this one C. Okay. And on the faces, you have 6 faces for here, 6 faces, 6 faces, 6 faces, a total of 18 faces. On the first dice, I wrote the numbers here. The points here are 3, 5. So you have 18 faces, and you have to put. I'm going to put 18 numbers from 1 to 18. All the numbers on the faces of these 3 dice. A is composed of 3, 5, 7, 12, 14, 16. B has 2, 4, 9, 11, 13, 18. And the C has 1, 6, 8, 10, 15, and 17. You can check that you have all 18 numbers here. None of them is repeated. And this is, it belongs to Alexander. This one belongs to Bruno. This one belongs to Caroline, or whatever, or Carol. And they are playing. They are throwing dice, and they want to see who is winning, who is getting better scores. Let us first look at Alexander and Bruno. This and this. Okay, so we have, these are fair dices. There's no trick. So this is, let's call this is A, this is B, and A can have 3, 5, 7, 12, 14, 16. B can have 2, 4, 9, 11, 13, 18. So Alexander and Bruno throw the dice, and if Bruno gets a 2 and Alexander gets a 3, Alexander wins. If Bruno gets a 2, Alexander wins any case. In this case, Bruno wins. In this case, Alexander wins. Okay? And here we have Bruno wins because he gets a 9, Alexander on 3, B, B, B, A. And for Bruno, you get 11, B, B, B, B. Oh, no, A. Alexander has 12 here. A. Here, B, B, B, B, A. And here, all the way B. 18 is the highest number. Okay, so who wins most often? As you see, of course, each outcome has probability of 1 out of 36, right? So the probability that we have this is 1 out of 36. So Alexander wins 1, 2, 3, 6 of them. 6, 5 plus 11, 14, 17, 19. Alexander wins 19 out of 36 times. Alexander. And Bruno wins the remaining times. 17 out of 36. So Alexander wins most often. A little bit more. The game would be fair if it were 18 out of 36 and 18 out of 36. As it is, the game favors A, right? Because this is bigger. So A will have more luck in this case. He will win more often than lose. Okay?
Yes.
Okay. Now, as a homework, I want to compete B and C and A and C. C and A, let's say. Who wins in the game of B and C? Who wins in the game of C and A? So you'll be most amazed. And then if you can, try to find something amazing with 4 dices, A, B, C, and D. Maybe do it now. Compare B and C. Who wins in the game of B and C? And then C and A. I'm sitting here and I wait for your answer. So if you compare B and C, you see that B is better than C. If you compare C and A, you see that C is better than A. So A is better than B. B is better than C. And C is better than A. It's strange, yes? You have A better than B, B better than C. So you expect that A would be better than C. No, C is better than A. So as you see, sometimes the best is not easy to determine. You should all do the calculations though for CNA, like do a board like this and see that C is better than A. A is better than B, B is better than C, and C will be better than A.
I think it's about which player is starting, maybe.
Which player is?
Starting the
There's
game.
no starting at all. There's no starting at all. There's only one dice. A third person, God, throws the dice.
Ah, okay.
But
Okay,
there's
so
no. Okay, so this game is is advantageous to A. This game is advantageous to B, and this game is advantageous to C. A is better than B, B is better than C. Now, when you see this, you expect that A would be better than C. No, C is now better than A. So the question would be now, can you do this for 4 players? A, B, C, and D. A better than B, B better than C, C better than D, but D better than A. Now, of course, you will have 24 numbers instead of 18. This may be homework. If you don't like math, well, you can write an essay about being better. What does mean being better?
Sayıları rastgele mi seçeceğiz hocam?
Efendim?
Kübün üzerinde yani D için olacak sayıları rastgele mi seçeceğiz yine?
Rastgele olur mu? Ben bunları rastgele seçmedim ki. Rastgele seçersen olmaz ki. Doğru seçeceksin. Bu sayıları doğru seçmezsek, bunları böyle seçmeseydim eğer, bu istediğim olmazdı. Buraya şey koy, A'ya
Ardışık.
1, 2, 3, 4, 5, 6 koy.
Çıkmıyor,
B'ye
evet, denedim.
7, 8, 9, 10, 11, 12 koy. C'ye de 13'ten 18'e kadar koy. A, B'den daha büyük, B, C'den daha büyük. A da C'den daha, pardon, tam tersine. B her oyunu kazanıyor. Bu da C her oyunu kazanıyor. C herkesten daha büyük. Burada hiç şaşırtıcı bir şey yok. Bu şaşırtıcı olanı A'nın daha iyi olması, B'nin C'den daha iyi olması ama C'nin de A'dan daha büyük olması. Demek ki burada daha iyi, iyi olmak, yenmek transitif, geçişkenli bir ilişki değil. Geçişken demek şu demektir. X Y'den büyükse, Y de Z'den büyükse o zaman X Z'den büyük oluyor. Bu geçişken demektir. Bu oyun geçişkenli, bu oyunlar konumu geçişkenli değil. Mesela en iyi satranç oyunu. En iyi satranç oyuncusu. Şimdi A her zaman B'yi yenebilir. B her zaman C'yi yenebilir. C de her zaman A'yı yenebilir. Çünkü satrançta oyun açılışı var, oyun ortası var, oyun sonu var. Değil mi? Yani farklı yetenekler var satrançta. Tabii onu yapıyorlar, biraz hile yapıyorlar. Her oyuncuya bir puan veriyorlar. İşte en iyi oyuncular 2000 üstünde, 2400, 2600 falan puan olanlar var. In chess, speaking English. In chess, for example, a player A may always win against B, or most often say. B may win against C. So you say A is better than, let's say A wins over B, B wins over C. So you say A is better than B, B is better than C. Then you assume that A is better than C. No, it may not be true. Because in chess, you have several staff. For example, some players are good in the beginning of the games. Some players are good in the middle game, the most complicated, with most pieces. They are very clever, very ingenious. And some players are very good in the end game. End game, you have very few pieces left. 2 pawns against a knight and a bishop, for example, something like this. And it's a question of computation. You calculate, you compute. For example, the computers are very good in the end games. There's no way you can beat a computer in the end game. And in the opening, in the beginning, in the first 10 moves, it's very difficult to obtain an advantage over a computer because computer knows all the openings. the computer read hundreds of books. It has all the details in his memory. So in the beginning, the opening is very difficult to beat the computer. Not to beat, but to have an advantage over the computer. And what do the best players? They try to have an advantage in the middle game, when the game is too complicated, so that the computer cannot compute anymore as effectively as in the beginning or in the end. And they try to do the good players, the best players, when they play against a computer, against a good computer, because the bad computers, they can win easily. The best players, they do a move that the computer doesn't expect. What does mean the computer doesn't expect? It means that the computer doesn't have it in its memory. In its memory, they say, if the player plays this, then you do this. If the player plays this, then you do this. And the good player does something that thinks that computer doesn't know, did not have time to analyze. But lately, you know that computers win, unfortunately, against the best players of the world. It wasn't so a few years ago, but now computers are much stronger than humans. Also in Go, in the game of Go, computers win against the humans. Go is much more complicated than chess. As a game, it's simpler, but it has much more combinations. Number of combinations is huge. It's way away the number of computations of chess. So the computers were not so good in the game of Go. So humans beat them very often. But lately, they've done a program, and a young player, a young Japanese, Chinese, or Taiwanese, I don't know, a young player, he is not only the best player of the world, he is also one of the two best players of humanity, of the whole humanity. He lost. It was very sad. It was a sad day for humanity. Okay. I wish you enjoyed this course, the ones who were here.